In this video, we're going to look at the applications of parametric equations to nonlinear motion. That brings us to the realm of doing some more physics problems. And so let's say that we're trying to model both the horizontal and vertical positions of an object that is launched. And in order to do so, we're going to have to create and look at a vector here. So let's say I have my object. That's right here at this dot. So this is my object. And it is launched along this vector here. And so this vector will be the velocity vector for the object. So that's going to be my initial velocity. And so the magnitude of this vector is going to equal the initial velocity. So that's going to be v naught. And remember that vectors have both magnitude and direction. And so for this vector, what we're going to do is I'm going to draw a horizontal. And it's going to be launched at some angle of theta here. And so the angle is going to be theta. And we're going to break up and look at the horizontal and vertical components. So I'm going to make a right triangle. And we're going to write the horizontal and vertical components. Well, the horizontal component, which is going to be the effect that it has in terms of its horizontal position if this object is moving. This object with nothing acting on it is going to have an x component of initial velocity, magnitude of the vector, times cosine of the launch angle. And the vertical component, which I'm going to say y of t, can be represented kind of the same way. It will be initial velocity times sine of the launch angle. And that brings us to the component form of the vector for the launched object. So it would be v naught cosine of theta by v naught sine of theta. So initial velocity times cosine of the launch angle times initial velocity times sine of the launch angle. Now, assuming that nothing else is acting on it, no wind, no external forces, we're going to create a horizontal position equation based on time. And so it comes off of the formula distance equals rate times time. So d equals r times t. And we're looking along the horizontal, so d is going to be x, so x of t. Rate is going to be, in this case, the horizontal component of the velocity vector, so v naught times cosine of t. Now, to get the overall distance, I'm going to have to multiply that velocity per unit of time. And so it's going to bring us to an x equation where I can figure out where is the object per unit of time based on its velocity, initial velocity and launch angle. Well, that would be initial velocity times t cosine of the angle of launch. So we can model horizontal position with that. Now, simultaneously, we also want to do the same thing for vertical position. But in order to do that, we're going to have to take into account gravity, because gravity is going to act on the object. And what we're going to do is we're going to use a physics equation where I can determine the vertical position of an object by looking at the acceleration due to gravity, which is g. And so it'll be negative g over 2 times t squared plus h naught, where h naught just stands for the initial height of the object. And g being the acceleration due to gravity, that would depend on what planet we were talking about, but we're going to do all of our applications in class here where we're on Earth, and which g is equal to 9.81 meters per second, or we can say in feet per second, which equates to about 32.17 feet per second. Now, to simplify this a little bit farther, we're just going to use, let g be equal to 32. And if I put in 32 where g is, that gives us our falling body model to be negative 16 t squared plus h naught. We can account the vertical component of the launched object, meaning the vertical part of its velocity. Now, we would refer back to our vector. And we see that the launched object will have the vertical component of velocity of v naught times sine of theta. So we also need to go into our distance formula. So distance equals rate times time. And look at the distance that this object would want to go along the horizontal if nothing else was acting on it. And that would give us d equals v naught times t, so initial velocity times t sine of the launch angle. And we're going to take that and we're going to add that in to our equation, which will give us our y parametric equation to model this motion, which would be equal to negative 16t squared plus the effect of the launch object, so v naught t sine of theta, plus the initial height. So there's our y parametric equation. So the parametric equations we're going to use for nonlinear motion, which means it's not going, we're going to say it's not going straight down. It's going to have some kind of curvature path to it. And we're going to stay in feet per second in class here, and we're going to model with those two equations. Our first application problem for parametric equations, we're going to do a football example. So I have a football kicker, in this case Josh Pack, and he wants to know how far can he kick a field goal under different playing conditions. Now, there's some things to keep in mind. All right, so over here on the right-hand side, we'll have our kicker, all right, my little stick man, and he wants to kick the field goal, and our field goal here, some distance off to the side. The field goal has a height, the crossbar that it has to clear has a height of 10 feet. And he's going to kick the ball off the ground. And so we want to know how far can he kick it based and clear that crossbar for different conditions. Now, what we do know is that he's kicking the ball off the ground. So we have an initial height of 0. And the ending height, it has to be 10 feet, I guess, by the time it gets to the field goal. The initial velocity is already in feet per second, so initial velocity is equal to 60 feet per second. Now, we're going to go ahead and set up our parametric equations here. So we know that parametrically we can define this motion as x of t is equal to initial velocity times t cosine of the launch angle. And my y parameter can be defined as y of t is equal to negative 16t squared, because we converted this and we rounded it so that way it'd be in feet per second. That's where the negative 16 comes from. Plus initial velocity times t sine of theta, plus the initial height. Well, the initial height's 0, so I'm not going to write plus 0 on the end there. Now, we can't graph these equations because we have too many unknowns. We don't know what the launch angle is, so we can't graph this set. But what we do know is that at some point down the road, after he kicks this, the ending height has to equal 10 because that's the height of the crossbar that it has to clear. So what I'm going to do is I'm going to take that y equation and I want to rewrite it for theta equals, so that way I can substitute it back into my x equation. And so after I do that, so I'd have a process. I'd have to add the 16t squared to the 10. So it'd be 10 plus 16t squared. And then I'd have to divide by 60t. And then take the inverse sine of all of that. And that's going to give me theta. Now, from here, in order to find a maximum, so we want to maximize the x distance. So I'm going to take my x equation, and I'm going to start writing it. So it'd be x equals 60t times cosine of, and then where I'm writing theta is where I'm going to put my theta equation that we just derived. So inverse sine of 10 plus 16t squared all over 60t. and that's going to give me my x position. And what I'm going to do is I'm going to graph that. So I'm going to go into Desmos, and we're going to graph that equation here. So we have the effect of no wind, and we're graphing it, and we want to know how far it will go. Well, Desmos, I'm going to let it be y equals a function of t here. And we just have to remember that really the y are x values in context of what we have. And you have to, part of this is you also have to set a good zoom window. So my window goes from about 0 to 5 on the x, and for right now, it goes from 0 to 120. We might have to adjust that later. And I see this parabola-looking curve. Remember, this is not the path the ball is traveling, the kick. This just represents horizontal distance, and I want to find the maximum of it. So then we'll go find the max. So the max of that curve occurs at 2.531 by 102.011. Well, the first number is time. That's the time of flight. So after he kicks it in 2.5 seconds roughly, it'll be at the crossbar. And the 102 is the distance traveled. So we have a critical pieces of information right now. So what we're going to do now is we're going to take that information where we have t. We now know that t is 2.531. And I'm going to put that back into my theta equation where the t's are. And I'm going to go figure out what the launch angle is. So this will tell me what angle he's got to kick the football at. So I put 2.531 back in for my theta equation. And we do that, and we're going to get theta is equal to approximately 47.798 degrees. Now, the distance that it traveled was the 102.011, which is feet. And for football, a lot of times it's in yards. And so if I wanted to convert that into yards, I would just divide it by 3, and he can kick the football 34 yards. Now we want to look and say, all right, now we want to add the effect of wind. So we have a 15 feet per second wind that's acting with the ball. And so the wind is going to act only along the horizontal. So what I'm going to do is I have to rewrite my horizontal equation. So x of t is equal to 60t cosine of theta. And now I have to do the wind effect, which means I'm going to do plus 15 times t here, because the wind is blowing constantly. And so it's going to be adding to the distance that the ball would travel. Now, the y equation remains the same as it did in the previous example for part A. So what I'm going to do is I'm going to take the equation that I already have for theta back in part 1. All right, and I'm going to resubstitute that back in for this theta, and I'm going to regraph. So we're going to find the max of x of t equals 60t squared, or 60t cosine of inverse sine of 10 plus 16t squared over 60t. And then we have our plus 15t on the end, which is the effect of wind. So we'll go back into Desmos and we'll regraph this one. All right, so I had typed in that equation with wind, and I get it all the way typed in there, and I make sure that I got my parentheses right, and I have the plus 15t on the end. And we look for the new maximum. Well, the new maximum here is going to occur at the coordinate 2.736 by 141.578. And I have to remember the 2.736 is t, and that 141 is distance in feet. So that's how far it went in feet. So with the wind acting on the ball, we want to determine what the launch angle should be. So what I'm going to do is I'm going to take that t and I'm going to put it back into that theta equals equation. So I'm putting in my t back into that theta equals equation back in part A. And then I'm going to get a new launch angle here. So when I do that, I get a new launch angle to be 52.23. Which means that when the wind's acting with the ball, he's got to have a slightly higher launch angle so that way the wind can continue to help it. And that distance it traveled, 141.57 feet, if I wanted to convert that back into yards. So I divide that 147.573 or 578 by 3, and the field goal now that he could possibly make expands to 47.19 yards. And lastly, part C, we're looking at the effect of the wind acting against the ball. So it's like the wind is blowing in his face. And so I have to readjust. The wind acts along the horizontal. So my X equation is going to become 60t times cosine of theta. And then the effect of the wind acting against the ball is going to be minus 15t. And so that is my new X equation. And I'm going to take that same equation that I had back in part 1, this inverse sine equation. I'm going to put that in where theta is, and I'm going to get a new equation to graph and find the max of. So I want to find the max of x of t equals 60t cosine of, and then I'm putting in that inverse sine of 10 plus 16t squared all over 60t. And then we have our wind effect, so minus 15t on the end. So that's what we're going to graph. And we want to find the new maximum here. All right, so go back to Desmos. We're looking, and I get this thing typed in. And you just double check that your parentheses are everywhere they need to be. And I got minus 15t on the end. All right, so it's back in there. And I have my new curve. And of course, I'm expecting this to be lower in height because the wind is acting against the direction of travel. And we get a new max of 2.261. So I have a max at 2.261 by 65.972. All right, so that is my feet, the distance traveled, and this is the flight time, the time that the football is in the air by the time it gets to the crossbar. And so to get the launch angle from here, I'm going to take that t that we got and do the same thing with it that I did with all the other ones. So my t's to get my launch angle are going back in to my theta equation where all the t's are. And when I do that, I get a launch angle. So when the wind's acting against the ball, or the flight path, of 42.582 degrees. So he has to kick the football a little bit lower to get it to go that maximum distance of 65.972 feet. And the distance in yards, if I divide 65.972 by 3, it goes 21.99 yards. So it doesn't go very far. In this example, we're going to look at a three-point shot in basketball. And so we want to know, with the given situation and how far away from the basketball hoop this person is, what would the launch angle or angles have to be for a successful shot, and figure out what the corresponding flight times are. And I'm going to draw a real rough diagram of what we have here. So we have our basketball hoop, and so I got my goal. And the basketball hoop itself is 10 feet off the ground. And this basketball player is going to shoot this basketball, and we're trying to make a successful shot. Now we do know that the distance along the horizontal from the center of the hoop to the release of the shot is exactly 20 feet away. along the horizontal. And that the initial velocity of this shot is 20 miles per hour. And that the release height of the basketball is 7 feet off the ground. Now, in order for us to write our set of parametric equations, everything has to be in terms of feet. And notice how our velocity is in miles per hour. So I have to convert my 20 miles per hour into feet per second, which means I would take my miles per hour, I would multiply by 5,280. And then divide by the number of seconds, which is 3,600. And that's going to give me about 29.33 feet per second. So that's going to be my converted initial velocity to write my set of parametric equations. So the horizontal position of this shot relative to the shooter is going to equal 29.33 t cosine of theta. There's no wind or anything to account for inside of the gym. The vertical component of this is going to be equal to negative 16 t squared plus initial velocity, so 29.33 t sine of theta, plus the initial height. Well, the initial height here is 7. And we know that we got to use the location of the center of the hoop. So the center of the hoop relative to the shooter, I treat that like a coordinate where the ball has to travel 20 feet along the horizontal and be 10 feet high. So 10 is y, 20 is going to be x at some point along the shot. Now, what I'm going to do is I'm going to take that 10, I'm going to put that 10 in for y, because we're going to need to substitute one of these equations into the other, so that way we can solve. And then I'm going to take that equation and I'm going to rewrite it as theta equals. Let me change colors. So that would become, after I do that, so I'd have to, so theta is going to equal the inverse sine of, and subtract the 7, so that makes 3, add the 16t squared over, divide by 29.33t. And so this will give me my theta if I knew what t's were. Well, we're going to take that equation, we're going to plug it into our x equation and graph. So we're going to graph, I'm going to get a different color. So we're going to graph x of t equals 29.33t times cosine of, and then that's where I'm going to put in for theta this inverse sine. Now, we also know that we're not trying to maximize distance here. It has to go exactly 20 feet. So at the same time, I'm going to graph x equals 20, and I'm going to look for intersections. All right, so we're going to put that into Desmos, those two equations. We're going to graph. And so I get Desmos pulled up here. And I get my two equations in. I got to type them in as y equals. To get Desmos to graph them correctly. And so to make sure I got it typed in right, and I do. And so what we're looking for is we're looking for the points of intersections between the horizontal distance curve. Now that's not the flight of the basketball, it's the horizontal distance curve, and for when it equals 20, and it happens at 2 locations. So, and the locations that I have, both of them have y values of 20, but it's the x values of these points that represent my flight times. So I have flight times, so I have one flight time of t equals 0.8359, or just say 0.836. And then I have another one that is t equals 1.512. And so I got that right off the intersection of the graph. Now I want to get the corresponding launch angles. Well, the launch angle for the shot here, so which angle she needs to shoot at, the launch, I need to take those t's that I have individually, and I need to put them into my theta equation where the t's are. And that'll tell me the angle at which this basketball player has to shoot the basketball at. And so for the flight time of 0.836, we plug that in, we get a launch angle of about 35.34 degrees. For the flight time of 1.512, get a launch angle that's a little bit steeper of 63.19 degrees.